and I'll introduce this husband and wife team. So you'll notice there's no social distancing going on there, but this is a married couple, Professor Claire Horwell and Professor Ed Llewellyn. They join us today from Durham University's Department of Earth Sciences to talk about Volcanoes and Society. Claire is founder and director of the International Volcanic Health Hazard Network. She's acted as an advisor to the World Health Organization, Public Health England, and the UK Cabinet Office regarding the respiratory health hazards of volcanic ash. She's been awarded the European Geosciences Union 2020 Plinius Medal for her outstanding interdisciplinary research on the respiratory health implications of volcanic aerosols. She's currently the president of the American Geophysical Union's new GeoHealth section. Ed is Professor of Volcanology, Management Board member in the Institute of Hazard, Risk and Resilience, a member of the Durham Centre for Soft Matter, and member of the Institute of Medieval and Early Modern Studies at Durham. He's the 2021 recipient of the Thermo Fisher Scientific Volcanic Magmatic Studies Group Award and the 2016 award of the British Society of Rheology. The focus of his research is to quantify the physical controls on the style of volcanic eruptions. Both are very well published, and it sounds like Durham is very lucky to have you on their staff. Indeed, we feel very privileged that you've taken time to come and talk to us today. So, thank you for doing that. Ed, I believe you're up first. So I will switch my sound off and we can get going.
Thank you very much for the introduction. Can everyone hear me? Yep, okay. Yeah. Yes, thank you very much for the introduction, and thank you very much for the invitation to come and speak to you today. We enjoy doing these sorts of outreach events, and it's nice to be able to communicate our science and our interest in volcanoes to people, and particularly to school children. Those of you who are interested in volcanology might be interested to know that actually it usually sits in earth science departments in universities rather than in geography departments. So obviously I realize I'm speaking in a geographical society talk here, but actually it typically falls under earth sciences. So if any of you do find yourself interested in studying a degree that includes volcanology, then you'd be very welcome to come to Durham, of course, to Durham Earth Sciences, or indeed to look at other earth sciences departments around the country. Oh, excuse me, having trouble moving my video. There we go. So yes, as you were told, I'm a physical volcanologist, which means I'm interested in understanding the physics of volcanic eruptions. And of course, the reason we try and understand the physics of volcanic eruptions is so that we can do a better job of understanding why they erupt the way they do, and then ultimately a better job of trying to predict volcanic hazards. And later on, after I finish speaking, Claire will talk more about impact hazards and risk from volcanic eruptions. So we're going to start with a game of Spot the Volcano. This may be a rather easy game of Spot the Volcano, I should say. This may be a familiar volcano to some of you. If I were to tell you that just over here, just out of view, is the ruins of the town of Pompeii, then probably it'll be a familiar volcano to even more of you. So this is Vesuvius, sitting above the city of Naples in southern Italy. And Vesuvius had its most famous eruption in AD 79. Here's a satellite image, first of all, showing the location within Italy, and then here's a zoom in on the Campanian region. Here's the city of Naples, and here's the volcano of Vesuvius. Pompeii would be around here. And the reason Vesuvius is so famous is because it was the first volcanic eruption to be carefully witnessed and recorded. So Pliny the Younger, the Roman naturalist, was sitting over here at Capo di Miseno, or Roman Misenum as it was then, and he was watching the eruption of Vesuvius unfold over a couple of days in AD 79, and he wrote down his recollections some years later, and they became recorded history. So this eruption of Vesuvius produced 3 cubic kilometers of magma, which had erupted mainly as ash and pyroclastic density currents. It's rather hard to get your head around what 3 cubic kilometers looks like. But if you were to spread that material evenly over Durham city, it would form a layer about 100 meters thick. So not just Peninsula Durham, but the whole of Durham city. So it's really quite a large volume of material that was erupted. But actually, this was a harder game of spot the volcano than you might originally have thought, because there are in fact two volcanoes in this picture. And Vesuvius is very much the smaller of the two. And the other volcano is much less obvious because it sits underneath the entire Campanian region, or much of the Campanian region. Much of it's under the Bay of Naples, and much of it underlies the city of Naples. And it's so large, and its eruptions were so explosive that it's just left a rather flat region, or in fact a region that's partly collapsed, which is much less obvious than the volcanic edifice of Vesuvius. But if we look on satellite imagery again, I've picked out here the outline of the caldera of this supervolcano. So a caldera is basically a hole left behind after a giant volcanic eruption. And you can see that it's many, many times. This is equivalent more or less to the crater of Vesuvius. So you can see how much larger it is. And this has had several eruptions, but the largest that we know about was about 40,000 years ago. And that produced 300 cubic kilometers. So that's 100 times more material, again, mainly ash, than the eruption of Vesuvius in AD 79. And that's even harder to visualize, but this time, if you covered the whole of County Durham, not just the city of Durham, if you covered the whole of County Durham, that would form a layer 100 meters thick. So it's really a stupendous amount of material that was thrown out by this eruption, and indeed enough to change climate quite substantially. So the purpose of that exercise was to demonstrate that although some volcanoes are quite obvious, not all of them are, and volcanoes have quite a wide variety of different shapes, or what we would call morphologies. Here in the top left is the classic conical volcanic edifice. If you asked a child to draw a volcano, they'd probably draw something a bit like this. This is Mount Fuji in Japan. This is quite a large volcano. Over here in the top right is something that looks much less impressive, but is in fact the largest volcano on Earth, and indeed the largest edifice of any sort on Earth. This is Mauna Loa on the big island of Hawaii in the US. And from a distance, it just looks like a rather unimpressive low hill, but actually it's 4,200 meters above sea level and more than 8,000 meters above the surrounding abyssal plain of the Pacific Ocean. So these are two large volcanoes. This is the very largest volcano on Earth, and they're produced over hundreds of thousands of years by repeated eruptions at the same place. But that's not always the way with volcanic eruptions. Sometimes a volcano will erupt just once and that's it, it'll never erupt again. And these volcanic scoria cones or cinder cones down in the bottom left from the Auvergne region in France are an example of that sort of eruption that only happens once, and they form typically much smaller volcanic features. Over here on the right is an example of one of the very largest volcanoes on Earth. This is, or largest supervolcanoes on Earth. So this is the same sort of volcano as Campi Flegrei. This is Toba, the Toba supervolcano on the island of Sumatra in Indonesia. And this is stupefyingly enormous. This is 100 kilometers long, this depression, and this lake sits inside the caldera of an enormous volcanic eruption about 75,000 years ago. And that's one of the largest volcanic eruptions for which we have good evidence. And to give an idea of the scale, if Newcastle was sitting down here on the southeast corner, then Carlisle would be sitting over here on the northwest corner. So this is a really huge feature. So volcanoes come in many different styles and sizes and shapes. So they're not always as obvious to see as you might think. Nonetheless, modern volcanology believes it's found more or less all the volcanoes on Earth. And this map plots them. First of all, on top of this map, I've overlaid some of the volcanoes that we've just been talking about. If I remove those, then you can see that volcanoes are not randomly distributed over Earth. They're in fact clustered in a few different sorts of geographical location, the most obvious of which is this Pacific Ring of Fire, which I'm sure you'll have heard of. So there are volcanoes all around the Pacific margin. There's also some volcanoes within continental interiors, One of the most obvious examples is here in the East African Rift, which I'll talk about a little bit more in a moment. But we also get volcanoes in the middle of tectonic plates, in the middle of oceans, in the middle of continents where you might not otherwise expect them. And the Hawaiian Islands are a good example of that. This map also shows the largest series of volcanic features on Earth, which might not be immediately obvious, which is the mid-ocean ridge system. So in fact, about 80% of the Earth's magma output is through the mid-ocean ridges, but those eruptions take place in between 2 and 4 kilometers depth of ocean, so out of sight, out of mind. But from a planetary perspective, those are the most important volcanoes on Earth. One thing that we have identified, or one thing that modern plate tectonics has allowed us to do, is to understand why we find volcanoes in different sorts of environment, different sorts of geographic location. So I've talked just now about the mid-ocean spreading ridges. These are places where the oceanic lithosphere is pulling apart, and as it does so, the mantle underneath wells up to fill the gap. As it rises, it decompresses. As it decompresses, it melts, and it forms magma, which then infills the gap through volcanic eruptions and intrusions at the middle, at the mid-ocean ridge. A similar thing takes place sometimes in continental interiors. Over here on the right-hand side, we have a continental rift zone, and this is where a continental plate is starting to pull apart. This is the earliest part of the formation of a new ocean basin. And again, as the lithosphere pulls apart, the mantle wells up underneath and produces magma. So this would be what's going on in the East African Rift at the moment. As new ocean crust and lithosphere moves away from the mid-Atlantic, from the mid-ocean ridges, it becomes thicker and it becomes colder, and so it becomes denser. And eventually it becomes so dense that it drops down beneath adjacent tectonic plates and forms what we call a subduction zone. And as the subducting plate moves down into the mantle, it loses the water that it gained through a range of processes at the bottom of the ocean. And as that water comes off the subducting plate, it causes the mantle to melt, which sounds a bit counterintuitive, but it's a bit like the process by which ice melts when you throw salt on it. As water moves into the mantle, it causes those crystals to melt and produces magma, which forms subduction zone volcanoes, either in a continental setting or in an ocean island setting when that magma is coming up through another oceanic plate. And one thing we can identify is that the type of volcano and the type of volcanic eruption that we have is quite strongly associated with the tectonic setting that the volcano is in. So first of all, I've picked out some volcanoes that are subduction zone volcanoes, and I'll talk about each of these briefly. And all of these show or have shown explosive volcanic eruptions, which is quite characteristic of subduction zone volcanoes. So this, in a moment when I hit play, is a video of an eruption at Colima in Mexico. This was in 2017. This is a very small volcanic explosive eruption, but it's a really nice bit of footage. This is the peak of the volcano, this is the crater, and this is webcam footage. So it's sped up quite significantly because it was probably only taking 1 frame per second. When I hit play, you'll see it starts with a big explosion. Actually a rather modest explosion by volcanic scales, and that produces a lot of fine particles of ash. This is the same thing, rather slower. Those ash particles are thrown up into the air, and they're very hot, and because they're small and hot, they rapidly exchange their thermal energy with the surrounding atmosphere, which is entrained in amongst the ash. So it heats up the air then rises buoyantly, and it forms this lofting pillar, much like smoke rising above a chimney, except it's not smoke, it's ash and air. And Claire will talk quite a bit more about volcanic ash in a moment. One thing that's really notable about these explosive volcanic eruptions, or these eruption columns, which we call Plinian columns when they're large, after Pliny the Younger, who was the Roman historian who described the eruption of Vesuvius in AD 79. One interesting feature is that they're very similar across an enormous range of scales, which tells us that this process there's something universal about it for explosive eruptions. So this is a still image of the Plinian eruption of Pinatubo in 1991 in the Philippines. This is the largest eruption that's happened in my lifetime. And this produced about 5 cubic kilometers, some say up to 7 cubic kilometers of ash. which is about twice as large as the Vesuvius AD 79 eruption. And you can see this characteristic broccoli sort of shape of the eruption column rising above the volcano, which is obscured in cloud in the distance. At the other end of the size spectrum, this is a tiny little explosive eruption from the Soufriere Hills volcano in the West Indies in 1997. This is 10,000 times smaller than the eruption of Pinatubo in terms of volume, and yet it has almost exactly the same characteristics as the much larger eruption. Volcanoes in subduction zones, as I say, tend to be explosive. And one of the reasons they're explosive is because the magma that produces the eruptions is very viscous, it's very sticky. And that means that it can withstand a lot of stress, allow the stress to build up, and then eventually that stress bursts through and we get an explosive eruption. But it doesn't always produce explosive eruptions. And we'll look at an example here from Cinnabung, which has been erupting, most recent eruptive phase starting in 2014 and is ongoing. Again, this will be a movie in a moment. But just to clue you into what you're seeing, this is a close-up of the crater of Cinnabung. And within that crater is this large pile of dark material. This is very large. This will be at least a couple of 100 meters high and a couple of 100 meters across. So there's a very large volume of lava, very sticky, viscous lava that's piled up within the crater. And you can imagine taking a tube of toothpaste, putting it in your fist and squeezing your fist, and that viscous, sticky toothpaste would form a big pile on top of your clenched fist. Well, that's the same sort of process that's happened here to produce what we call a lava dome on top of this volcano. But these lava domes are very unstable, and sometimes they collapse with no warning. And we call these dome collapse eruptions or dome collapse events. And when they collapse, the lava is both very hot and it's very brittle, so it tends to break apart. And again, it forms blocks and fine ash. And these form debris avalanches that race down the side of a volcano. And we'd call this a block and ash flow, which is a type of pyroclastic density current. And these are very hot. This video taken at night shows that it's incandescent, the material, which means that it's at least several hundred degrees Celsius. And these are extremely destructive events, and all the more dangerous because they're hard to predict, because dome collapses can happen with no warning. This same volcano, Cinnabung, in 2018 had a large explosive eruption. In fact, it had another explosive eruption in August this year. But I've got footage of this. And there was a lava dome sitting up at in the crater of the volcano, but then there was also an explosive eruption through that lava dome, which produced this characteristic Plinian eruption column. There's a lot of scared-looking children here, but don't worry, everybody was okay in this video. It produced large pyroclastic density currents or pyroclastic flows that came down the side of the volcano. So these sorts of volcanoes that we find in subduction zones are capable of switching between eruption styles, between effusive and explosive eruption styles, which makes them particularly hazardous. I'm going to talk briefly about a very different style of volcanism, focusing on Kilauea in the Big Island of Hawaii, which is where I do most of my field work. So this is a basaltic eruption of low viscosity lava, which took place in spring and summer 2018. And here you can see a crack opened up in people's back gardens, basically. And from this fissure, there's a spewing of lava, which produced, first of all, a curtain of lava, and then it began to pinch off to produce smaller, more focused points of eruption, which eventually produced volcanic vents like this one you can see here. And the lava continued to squirt out of those, forming what we call lava fountains, which then fed lava flows. And these lava flows ended up destroying nearly 1,000 homes in the southeast part of Hawaii, including some places that my children had grown to love when we spent some sabbatical time there in 2014. So we were very sad to see this, but not as sad, of course, as the people who lived there. So as a physical volcanologist, I try to understand why volcanoes erupt the way they do. And this is a still image of an experimental kit, large-scale experimental kit that I built in a quarry near Durham in order to try and understand basaltic volcanic eruptions, so eruptions of low viscosity magma. And we've got a magma chamber down here, and then a transparent pipe, which represents the volcanic conduit that brings magma towards the surface and then erupts it. In the last video that you saw, you could see lots of magma and lava erupting, but what you couldn't see was that there was actually an enormous volume of gas being erupted as well. And that's a feature of all volcanic eruptions, that there's always lots of gas erupted. And so with this experiment, I wanted to try and understand how gas drives volcanic eruptions. So I'll show you a video of this experiment in operation. And what I did is I injected a whole load of gas into the magma into the analog magma chamber at the bottom of the conduit, and then videoed what happened halfway up and what was happening at the top of this experimental kit. In a moment, you'll see this start to play. So this is a simulation of a sustained eruption driven by the input of gas. So I've started pumping gas into the bottom, and you can see already it started to drive an eruption at the top because it's adding buoyancy into that column of analog lava. Then over here on the right-hand side, you'll see a large gas bubble starting to rise up. And when it reaches the top, it causes a big explosion because it's overpressured. And then behind it, you can see this trail of rapidly moving bubbles rising up behind it, which cause pulsations in this plume at the top, which are very reminiscent of the pulsations that you see in lava fountains. And so through these sorts of experiments, we're able to try and understand what it is that drives different sorts of volcanic eruptions. So I'll very happily take questions on any of this, but I'll take those at the end and hand over now to Claire, who's going to talk about volcanic hazards and impacts.
Okay, hi everyone. So yes, my research is kind of at the more human end of the volcanic spectrum, if there is such a thing. So I really look at what happens after an eruption happens, and how the eruption and its various hazards, which I'll talk about in a minute, actually impact society. So I don't know if you're aware, but actually around 10% of the world's population lives near a historically active volcano. So that means that there are a huge number of people around the world who are at risk at any one time of being exposed to the products of a volcanic eruption. So Ed showed you a much better map than this one, just showing you where the volcanoes are around the world. But I wanted to show you this one because at the top, in the top map, you see the volcanoes, and in the bottom map, you see population density of the world, so human population. And you can see that the darker shaded areas are where we have very densely populated areas of the planet. And so the red circles that you can see here represent where a number of volcanoes intersect with very high population densities. And so you can see that particularly in Central America, along the East African Rift zone, which Ed mentioned, in Indonesia, in the Philippines, and in Japan, we have a huge number of people who are at risk of being harmed in some way from the effects of a volcanic eruption. So let's look at what those actual hazards are which come from an eruption. So the hazards, I guess you could describe as the volcanic events which have the potential to damage people or infrastructure or the environment around a volcano. And the thing is that volcanoes really present a very special challenge to humans because we love them, right? They're beautiful to look at. They provide fabulous recreation facilities for skiing or hiking, but also the land around volcanoes tends to be very fertile. So it attracts people to actually use the land as their livelihood as well. And so that means that a lot of people tend to live near volcanoes. But the problem is that volcanoes may erupt very infrequently, and it means that past eruptions can be forgotten over the generations. And in fact, it's very possible to live near a volcano and not be aware that the mountain behind you is actually a volcano and could erupt. So it can be a great shock to communities when there's actually an eruption. And the problem with eruptions, I guess you could say it's a problem, and it's a difference between an eruption and, say, an earthquake, is that there are many, many different hazards that come from the eruption itself. And we'll look at those in a minute. And it's not just a question of there being many different hazards, but the scale of those hazards is so different. And some of those may be quite small in size, and some of them may be huge and could affect not just the local area, but the entire planet. but also the scale relates to the timing of that hazard as well. So some hazards may last seconds to minutes, whereas others may actually be a problem for months, years, or even decades after an eruption finishes. So there are many different things to consider when thinking about volcanic hazards. So this diagram here is a cartoon of volcanic hazards, and actually it's got pretty much all volcanic hazards on one diagram, and we would not expect most eruptions to actually be generating all of these hazards at once, and in fact there may only be a few of these hazards in any particular eruption. But most of them are probably hazards you've heard of before, and Ed's just explained about lava domes and pyroclastic flows, ash and lava and gas. And then there are risks of also landslides and also volcano-related earthquakes. So there's a lot of primary hazards, as we would call them. But volcanoes can also then generate secondary hazards as well. So this is when you have an effect which is a result of the eruption and is directly related to it, but may not actually be one of the volcanic phenomena. So for example, a tsunami might occur, as happened at Krakatoa a couple of years ago, where an entire sector of the volcano can collapse into the ocean and generate these large waves, as happened in Indonesia. We can also get fires generated when, for example, lava flows might set buildings or vegetation alight. We even get floods, and this happens where, for example, in Iceland, the volcano might actually erupt underneath an ice sheet. And finally, there's all the different kinds of damage to infrastructure. For example, roofs may collapse, which in itself is a hazard to the people living in those buildings. So trying to understand all these different hazards is really a key role for volcanologists. And there are many, many volcanologists who are working in volcano observatories or in universities whose job it is to think through and assess these different hazards and then think about the impacts for society. So Ed already mentioned that there are different kinds of eruptions, and so I mentioned that not every volcano is going to have every kind of hazard, and this diagram quite neatly explains that. So over here in the top right, you've got the more effusive eruptions that Ed mentioned, where you have a lot of lava being generated, like in Hawaii, and a lot of gas with it. And these types of eruptions tend to have actually quite low damage potential. And this could be expressed through a kind of volcano classification system called the Volcanic Explosivity Index. So these types of volcanoes or eruptions have low VEI. But then you can move into the more explosive kind. And of course, there's different scales of explosivity, from the quite low explosive volcanoes like Strombolian, which have Strombolian eruptions or Volcanian eruptions, a bit like the small eruption of Soufriere Hills or Colima that Ed showed you. And then you can also have much, much bigger eruptions. And then you move into this Plinian style of eruption that Ed mentioned. And that's like at Vesuvius in AD 79 or Pinatubo in 1991. And there's even a category called super Plinian eruptions or ultra Plinian eruptions. And these are the kind of super eruptions that you get, which are even bigger and would be off the scale of this slide. And it's these explosive eruptions that generate not just gas and sometimes occasionally lava, but also the ash, the pyroclastic flows, different kinds of debris avalanches, dome collapses, mud flows, etc. And so we would say that these kinds of eruptions have got very high or even extremely high damage potential and high VEI. So then we need to start thinking about, well, what are these hazards going to actually do to the surrounding environment and societies? And of course, it may be that the impact is so severe that it gets categorized as a disaster. And it's just worth saying that in general, the UN is trying to promote the idea that disasters happen to societies, that the hazard itself is the natural component and the disaster itself relates to the fact that society is there and that the people and the infrastructure involved may not be very resilient to the hazard. So we're going to think about that a little bit more. So first of all, we'll think about what impacts volcanoes actually have on societies. Well, this is quite a mind-bending thing to actually start to think about, because I've just told you about all these different hazards that could occur. And now you need to think about all the different aspects that we have built up in society. There are buildings, there are utilities, there's transport, environment, agriculture, health. And of course, every one of these hazards can have a different impact on each of these different sectors of our society. So how do we go about thinking about those? Well, we can break it down at quite a high level. We know that volcanoes can injure people, potentially even cause diseases, which is something I work on. But of course, sadly, people can also be killed directly by eruptions. So we know that there's a direct effect on people and their health. We know that buildings can be damaged and destroyed. So any kind of built infrastructure in our environment can be damaged by a whole range of hazards, but particularly the flows that come from volcanoes. And then we have the effects on what I call utilities. And this means basically the infrastructure which keeps our society going. So this is the electricity, the water, drinking water, sewage, communications. All of those can be impacted in different ways by different kinds of hazards, either being completely knocked out by flows or being damaged by acid rain, gases, and ash. And then there's the transport sector. Well, I don't know if you can see this tiny diagram in the bottom left here. There are so many different kinds of transport when you actually come to think about it. Of course, there's aviation and planes not being able to fly, like happened during the 2010 Eyjafjallajökull eruption. But of course, there's all the ground transport as well. And hey, even air balloons, hot air balloons. So there's all kinds of ways that different kinds of transport are going to be affected by all of these hazards. And then, of course, agriculture. And this is absolutely critical. People rely on agriculture for their livelihoods and in order to stay alive for their food. And so if agriculture is destroyed by different hazards and volcanic eruptions, that can have a huge impact on the society. And in previous centuries, vast numbers of people have died during eruptions or following eruptions because of starvation and famine. And finally, the super eruptions can have an impact in that they can actually change our climate. So if enough gas and ash is injected into the high stratosphere, then it can actually cause a layer which can eventually cause cooling of our climate for a specific, usually quite a short period of a couple of years, but it depends on the scale of the eruption and its duration. So in just one slide, I'm giving you an idea that there are many, many different impacts, and we can't go through the detail here, but we also need to think about how these impacts would really affect societies. And this is something that we've really started to think about in recent years and trying to actually work out, if an eruption happened now in this city, what is going to happen in terms of its effects on the surrounding environment. So let's imagine now that there's a volcano erupting in the city of Auckland in New Zealand. And the reason I've chosen this case study is because the volcanologists in Auckland set up a fantastic project where they got together with all the local utilities companies to try and actually work out and to plan what to do if there was an eruption. And the reason they're bothered about this is because Auckland sits on a volcanic field, around 50 volcanoes in fact, but each one is actually basically extinct because it's called a monogenetic field, which means that the magma comes up and erupts in one place and then stops. And then there'll be a pause, and then a few centuries later, probably, or even millennia, a new volcano in that field will come up. And so the last eruption here was 500 years ago, and it took place in the harbour. There's a beautiful island called Rangitoto, which is where this last eruption occurred. And the island is the edifice from that eruption. And so there could well be another eruption soon. And they decided to model an eruption taking place in Auckland Harbour, as you can see through this illustration here. And so the volcanologists came up with a scenario for the eruption, and actually it's quite a small eruption on the scale of things because that's what they would expect for that location. And then they modeled the impacts to infrastructure and utilities in the city. And when you start to think about it, it is super complicated. So just in this diagram at the bottom here, you've got the impact to an electricity supply network. And so when we think about it, when you generate electricity, there are loads of different components. There are turbines, motors, cooling equipment, etc. And any one or all of these could be damaged. And then, of course, the electricity has to make it from the generation plant via various substations and through wires and pylons to the consumer at the end. And again, any one of these aspects could be damaged. And so if you look at this table in the top left, they actually estimated through their modelling that even a moderately small eruption in Auckland, it could take a year to get electricity back. They also found that they would expect to have so much ash in the city that it could take more than 6 months to clear the ash from the city and to get the roads usable again. And here you've got an image just showing you what it might look like. This is from Sakurajima in Japan. And this is the city of Kagoshima, which is very close by. And they actually get frequent eruptions. And because of that, they're very organized. And you can see in the top right, there's an image of an ash collection point where people dump bags of ash in a predefined collection place. And then the city council collects that ash and takes it to a depository. And the thing is that you have to have somewhere in advance lined up, like an old quarry or something, where you're going to dump all this ash. So it takes years of planning. You can't just, well, people do just have an eruption and then it's complete chaos. But the point here is that it's possible to plan in advance and to plan for things like, for example, there being more than 2 years of raw sewage discharge into the city harbour. So you can see that even quite a small eruption can have a huge impact on society. And I mentioned this, it can also have an impact on health. And this is my own area of speciality. If you breathe in the ash, quite a lot of it will actually get stuck in your nose and throat. And this could give you a sore throat or a bit of a cough. But what we're worried about is ash getting into the lungs. And for that, the particles have to be really, really small, like less than the diameter, much less than the diameter of a human hair. And these very fine particles can get lodged in your upper lungs. And if you have existing diseases, like if you have asthma or bronchitis, then you might find that your symptoms are made a lot worse. So for example, if you're asthmatic, you might even have asthma attacks or bad wheeze. But we're also worried about ash getting into the very, very deep lungs, where our alveoli are and where our gas exchange system happens. And it's critical that this area stays open and free. And in that case, we start to get the concern of chronic and possibly fatal diseases happening, such as lung cancer, but also something called silicosis, which is related to the mineral crystalline silica, which might be in the ash. We're also worried about cardiovascular or heart diseases as well. The problem is we just don't really have the evidence at the moment that volcanic ash causes this, but we think it could do because we see these kinds of diseases in industrial exposures. So when workers are exposed to quarry dust, for example. One thing that is totally bizarre is that the longest word in the English language actually describes a lung disease caused by silica in volcanic ash. I'm going to attempt to say it. It's pneumono-ultramicroscopic silico-volcanoconiosis. And it turns out this is a completely fictional word. It was made up for a pub quiz or something like that. But somehow it's got into the English language. It is our longest word in the dictionary. And yet, as far as we know, the disease doesn't actually exist. But well, it was 2012 or so, the World Health Organization put out a report which basically said that any particles, any tiny particles that can get in the lungs might be able to cause a range of diseases, from heart disease to lung cancers, strokes, pneumonia, etc. And they estimated that 7 million people around the world die prematurely from air pollution. And this is mainly obviously from urban pollution and industrial pollution, but they also said that they believe that any crustal particles, and that would include volcanic ash, could cause this. Well, we're not really sure if that's the case, and particularly because eruptions, every time you have an eruption, as we've described, it can be so different. There's different magma, different scales of eruptions. And that means that the ash has different particle size, different surface areas, different minerals, different soluble elements. And all of this is going to affect if the ash is actually harmful in the lungs. And we just don't know. So a lot of my recent work has been about trying, instead of to work out if the ash is actually toxic when there's an eruption, trying to protect people and may help them be prepared instead. And this involves building resilience in a community. And resilience is really the ability of a society to bounce back when a disaster happens. And so we can achieve this resilience in different ways. So for example, we can have disaster risk reduction measures in place before a disaster happens to try and prevent it. For example, we could build a really high bridge over a river valley, like you can see down here, so that any flows coming from the volcano pass directly underneath and don't destroy the infrastructure routes. We can also make sure that we don't do silly things like building hospitals in the path of these flows. But unfortunately, that often happens, and it happens because people forget that this mountain behind them is actually a volcano. We can also really prepare communities. We can educate them about the hazards and about what to do when there's an eruption, how to interpret warning messages and what actions to take. And we can also have good evacuation plans in place. And then there's also a whole load of background things that we can do in a society to make it more resilient in the first place, to make people healthier, to make sure there's good medical facilities, that there's a low level of poverty, and that people have good livelihoods, and that also these livelihoods are somewhat flexible, so that if you can't work because you know, your shop has been destroyed during an eruption, that you've got some other way to earn money and to keep your family going. So I run something called the International Volcanic Health Hazard Network, and the idea of this network was so that it could produce the public resources to help prepare communities. And you can go to the network website at ivhhn.org, and this is what it looks like. And basically, once you're there, you can click on this public information tab, and then this takes you, oops, I didn't mean to actually open. I didn't think it was actually going to open. Let me take you back to the, there we go, back to the screen. I didn't realize that was a link, sorry. You click on that and it then takes you to a range of resources which you can then learn about eruptions and how to protect yourself. And these are aimed at the communities living near volcanoes. And even information about how to fit a face mask, which these days actually seems very appropriate. As well as having paper resources that people can print out and distribute within communities, we also have a range of videos as well. And one of these videos is called Life with Ash, and it's an account, it's an experiential film. So it tells people about what actually happened during an eruption at Merapi Volcano in 2010, when people had to cope with a huge amount of ash. And it's about how they actually did that. So this video has now had more than 10,000 views, and perhaps at the end of this, if we have time after questions, we might play it. But if we don't have time, then I really would encourage you to go and watch this film, and you'll learn a lot about what it's actually like to experience an eruption and to protect yourself and your family. So thank you very much. We'll move on to questions. I'll stop sharing.
Great, thanks so much to you both for that. Fabulous. It's great to see a few cameras on there. Thomas Carney and friends, good to see you with your masks on, sitting working together. Brilliant. I particularly like the scaffolding with the experiment always gets my attention. I can watch bubbles in that sort of thing all day. But how to deal with like electricity supplies in the event of an eruption. It's that sort of detail that's so useful to our year 12 and 13 learners. So thank you for all of that, the physical geology as well as the impacts on society. We do have a few questions. So, and there's a thank you from Gateshead College that they've got to go off to other classes. So let me just tell you that before we move on to questions. If anyone else has a question, please just pop it in the chat box or raise your hand electronically or physically if I can see you, and we'll get through as many as we can. So start with a relatively straightforward one first of all, from Colin, who asks, what does VEI stand for?
Yeah, shall I take that? Yes, sorry. I think I said it, but I should have written it on the slide as well. VEI is the Volcanic Explosivity Index. And it's a kind of qualitative calculation of the explosivity of an eruption that's actually taken from a few different parameters, such as the scale of the eruption. So the plume height is used sometimes, and the magnitude of the eruption is also calculated. And at the end of that, you can kind of get an idea of the size of the eruption. And it's on a scale of 0 to 8.
Okay, great. Thank you, Claire. And one from Thomas Carney. What factors cause the different types of eruptions to occur? How long have we got?
Yeah, great question. If you do come to Durham University and do the volcanology course, then we'll spend 4 weeks talking about that. So it's quite a complicated question, but broadly, I mean, at its broadest, it is quite simple. We tend to get more explosive eruptions the more viscous, the more sticky a magma is. I said that very briefly in the talk, but
oh, we've lost you a second there, Ed. I think the internet's playing up and your screen's frozen. Let's just see if it picks up again.
It's fine here.
Okay, there. Yeah, we can hear you again.
Okay. So I'm not sure how far I got, but basically it comes down to how viscous the magma is, how sticky the magma is. And the reason that matters is because magma has bubbles in it. It's bubbles of gas that drive volcanic eruptions. All of you will have seen the experiment where you drop Mentos into Diet Coke and it sprays out of the top. The reason for that is that Diet Coke is a liquid that's got gas dissolved in it, which is CO2 in that case. When you drop the Mentos in, it causes that gas to rapidly come out of solution, forming lots of bubbles, which change the volume of the liquid and drive it out of the bottle. A similar thing happens in a volcano. The gas that's dissolved in magma is mainly water, which of course at magmatic temperatures wants to be a gas. And you can dissolve perhaps 5 weight percent water into magma. As the magma rises, it decompresses and the gas wants to come out of solution in the same way that when you pop the top of a champagne bottle, the drop in pressure causes bubbles to form. Those bubbles grow as the magma rises. If the magma is high viscosity, i.e. it's sticky, the bubbles can't grow as much as they want to. And so they're like little bombs. They have a high pressure inside them. And when the magma erupts, they explode and they cause the magma around them to fragment. In the case of a low viscosity magma, where the magma is runny, the bubbles can expand and they can coalesce with one another and join up to form big bubbles that rise through the liquid, like in the experiment in the quarry that I showed you. And so they tend to, because you're losing the gas from the magma, they tend to be less explosive because it's the bubbles that drive the explosion. So at the highest level, the difference between an explosive eruption and an effusive eruption is whether or not the gas can escape easily. In an explosive eruption, it can't, and so the magma blows up, and in an effusive eruption, it can.
Okay, great, thank you. So a related question, and then I've got a request for just access perhaps to your PowerPoint or an idea of where you've got some of the diagrams and illustrations from.
We're very happy to send a copy of this. It's quite big. We could try and optimize the file size. It's about 200 megabytes, I think. But we could put it on a file share site. And if we send it to you, then perhaps it could be distributed that way.
That's great. We've got a Dropbox, so we could perhaps use that. So that would be great. Thank you. So I've got one more question at the moment. I think another one might have just popped through. So how easy, says Luke, this is from Luke Heath, how easy is it to predict the type of eruption that is likely to occur?
Oh, tricky. I mean, I'll say a bit about that, but you might have something you want to add to that, Claire. How easy? It depends. So for some volcanoes, it's very easy to say what sort of eruption it will be. So if you take Kilauea on Hawaii, almost all of its recent eruptions have been oozing lava flow forming eruptions. Sometimes it produces lava fountains, but mainly they will be low energy eruptions that are not going to form explosions. Occasionally, however, it does form explosive eruptions. Other sorts of volcanoes, like Montserrat, in Super Hills Volcano in Montserrat, that tends to form either lava domes or minor explosive eruptions. So for a given volcano, if you understand its eruption history, which is something that field volcanologists do by looking at the deposits left behind by previous eruptions, or indeed you can look at records from the volcano monitoring era, then the past is the key to the future. So if you understand the previous sorts of eruption at a given volcano, it's likely that future eruptions will be similar. Now, predicting what type of eruption a specific eruption might be. So if your seismometers are picking up ground tremor around a volcano, your tilt meters are showing the volcanoes expanding, you might think an eruption's coming. Predicting what that eruption will be like is really hard. And even harder is, once an eruption started, predicting when it's going to end. So that, of course, was the question on everybody's minds when the Eyjafjallajökull eruption was happening in 2010. Everybody wanted to know when it was going to stop so that flights could resume. So again, a complicated question with I'm afraid a complicated answer, but it's difficult is the one-line summary.
Yes, great. Thanks very much. I don't see any other questions through chat. There's a few email addresses coming through with details for certificates of attendance, which is great. If there's anyone still online that would like to ask a question, now's your chance. I've launched the poll as well, so if you can just take a minute or two to answer those two simple questions. We're just trying to find out how you heard about today's talk and also how many of you are watching there today. So while we just see if there's any last minute questions to come through, I'd just like to thank Professors Horwell and Llewellin. Thank you so much for your time today. It's so interesting, and to have such a tale of two halves that complements each other so well, for all the physical geographers and geologists out there, and then the human side of it as well. I think it just works brilliantly. So thank you very, very much. That's great. Thank you. For those of you who are regulars, you'll know we've got our next talk on Monday afternoon. For those of you who are not, it's on the Ousbourne Valley. You're very welcome to sign up. Just drop a note in the chat. I'll leave that up for a little while and put our contact details up for the GA. So keep in touch if you're interested in more of our talks. Thank you again, Claire and Ed. It's been an absolute pleasure again today. Makes my day, and so organises some lessons for me, I have to say.
Our pleasure.
Stay safe in Durham.
Thank you very much.
You too.
And thanks everyone for coming along. Bye-bye.
Bye.
Bye-bye.